All right, so this is episode 2 of our Cosmos Safari podcast, and back with us is Rob Webb.
Here I am.
Welcome, Rob. How are you doing?
Doing all right. Just got back from a trip to Colorado with my family. Just absolutely gorgeous out there. We got to go through the Rocky Mountain National Park. We did that. I forget what road it is, but it goes up and multiple switchbacks. It's just absolutely gorgeous. I hadn't been out west like that, and to see how big those mountains can be and how you can see avalanche evidence, you can see where the forest fires were. It was just gorgeous. Got a couple astro photos too, which I'm still kind of
cool
looking through. So I'll have to share them with you sometime in the future. But it was just absolutely cool. Plane rides were smooth, so I'm happy. So
awesome.
All's pretty good. How about you?
I am doing well. I have just got back from Chicago. I did a NSTA, National Science Teachers Association conference with simulation curriculum, and talked all about the Starry Night software and Sky Safari software that they use and publish. Had a great time, lots of interest. So let's talk James Webb Space Telescope today. The James Webb Space Telescope, if you don't know,
Named
folks,
after me.
is the brand new observatory that NASA, ESA, and I think Canada are the main yeah. So NASA
contributors.
Yeah, NASA is the main contributor, and then ESA and the Canadian Space Agency are all involved in James Webb. So that launched a few months back, and we are just now seeing the first data from that with the images. So most people have seen that if you've been paying attention online. Today we're going to talk about that, as well as some of the future of James Webb and what we're excited about.
Now, before we start, I want to start off with a little quiz for you. Just two. I'm going to put you on the spot here. Okay. And these are just two questions that I thought would help inform what I have prepared as far as expectations.
You've prepared things.
I've prepared things.
Nice.
Imagine that. So first quiz. Okay. First question. What year is multiple choice? This one's multiple choice.
Hey.
What year was Hubble launched? Was it 1983, the year that I was born? Was it 1990? Was it 1991, when Nirvana's Nevermind, Pearl Jam's 10, and Metallica's Black Album were released, the best year for music that's ever been? Or was it 1994, when Green Day released Dookie and the CD was passed around my elementary school classroom because it had naughty words on it?
Oh my. Oh, this is hard. I am going to say 1991.
Oh, you're so close.
90.
1990.
I was going to go with 90, and I decided not to. I knew that there was the 30-year anniversary.
Yeah.
So I knew it was at least that old.
Right.
Okay.
But yeah, so 1990. So just think, we've had Hubble up there for 32 years. That's a good thing to think back to when we're talking about Webb.
Right.
And lastly, how old is the universe?
Ooh.
And you can give me as many significant figures as you'd like.
I'll just do one, because I would say that second decimal place, so 13.8 billion is the number I'm going to go with, because I've seen the other one change every few months for most of my career. So right. I'm going to say 13.8.
That's good. You're less than 1% off. Right now, it looks like it's 13.787. So it's 13,787,000,000, give or take 20 million years.
Okay.
So you are well within the range. Well done.
Nice.
I would have said 13.7.
Okay. But yeah, 13.8 is the number that just came to mind. I'm pretty sure that that's going to change with Webb telescope data. We'll see. Maybe not.
Yeah. So that gets me into what I have prepared here, which is, what are we excited about with James Webb? Why did I make my son, he did it willingly, but why did I make my son wake up on Christmas morning to watch this thing launch? Why did I do that? Right. And that's one of the things about science is, number one, it's the questions that we don't even know that we are going to ask.
Right.
We have a whole set of stuff that we know we're going to find, or that we know we're going to investigate. But there's going to be all kinds of things that we don't know that we're going to find that are surprises, and we're going to adjust things. I think that's the best part of the science. You find the answer to why or how, and then you think, well, why or how is that the case? And it just keeps going down and down and down. And I have an example from Hubble. There was this Hubble Key project that concluded that the Hubble constant, I'm not going to go too deep into that, but the expansion rate of the universe was 72 plus or minus 7 kilometers per second per megaparsec, right? But that was something that wasn't what anybody expected. Apparently, there was a team that thought it was something like in the 40s or 50s. There was a team that thought it was in like the 80s, 90s, and turns out 72.
Yeah. Yeah. Right.
Like it's interesting. And the interesting thing too is, like, one group says this, one group says this, we figure out somewhere in the middle, and then, okay, we just give up on those two wrong answers and we go with what we found the evidence for.
Exactly.
Which I think is amazing. We found the other moons of Pluto, like, Charon or Charon, like we already knew that one, but then we have Nix, Styx, Kerberos, and Hydra. We didn't know we were going to find that. Hubble Deep Field, which I actually have a picture of up there. The Hubble Deep Field and then the Hubble Extreme Deep Field. It found 5,500 galaxies in a region that takes up just 1/32 millionth of the sky. That's the Hubble Extreme Deep Field right there. And so when you add in what we know about galaxy formation and the expected, population of small galaxies that are too faint or too distant to be seen, I mean, we're talking an approximate 2 trillion galaxies within the observable universe, right? Now, the cool thing about this, though, too, this was not planned when Hubble was launched. This was somebody gave a presentation about this at one of our astronomy meetings, where basically this was a risk. Somebody was like, let's just find a spot.
I think I may have done it. It's hard to remember. Yeah. I did so many presentations for that, for our club. Mm-hmm. But yeah, it was part of, the director of NASA at the time has discretion over a certain number of the hours for Hubble. And I knew that that's going to be the same as well for James Webb Space Telescope, where they're allowed to choose what it is to observe. And that was the idea, is to pick a patch of sky that appeared to have zero in it, nothing at all, and just expose that part of the sky continuously for, I think it was about a month.
Yeah. And
that's the result that they got. The Hubble Deep Field.
And so that's the stuff that we didn't know we were going to find.
Right.
I got one more. If you switch, it's the gravitational lensing, which I know that there were predictions about this, right? But we had never taken pictures of gravitational lensing before, and Hubble was able to do that. Right there, what you're looking at is the ring around that sort of star in the middle. That is a far off distant galaxy that is behind that yellow orangish star, but because of the gravity of that star, or of whatever that is in the foreground, it bends and sort of makes a lens. Gravity makes that into like a magnifying glass.
I think what we're actually looking at is a very large galaxy. It's a spherical galaxy.
This is a spherical galaxy with some sort of a spiral galaxy behind it?
It's hard for me to determine what exactly that other galaxy looks like because of all of the distortion, but you're probably right. Yeah, it probably is a spiral galaxy or something.
So, I mean, that's really my big thing here is, what special, interesting, risky observation will we make with Webb? Here, you know what? Let's take a look at the pictures that they did. And this is actually on Hubble site, or sorry, Webb site, Webb.
It's the website for web.
Of course, I haven't heard that one a million times. But so this is a cool thing. It's got sliders that actually help you see the difference between Webb and Hubble.
Wow.
And it is just ridiculous. And so take a look at the actual images that they came back and compare them to what Hubble did, which is why I brought up Hubble in the first place in that quiz. So you're taking a look here at a planetary nebula, right? So the star that exploded and is pushing out this gas bubble. And, because Webb is so much bigger and it takes different light, right? It takes more infrared stuff. You start seeing something a bit more, you get more background stars. But then just look at that detail.
It's crazy.
And I'll put it right in the middle there, right? I mean, just, it's less fuzzy. It's more resolved. And you can see more detail going out farther, that just consider the difference of what you can learn from a picture taken with your cell phone versus a picture taken with like a telephoto lens and, really good.
You just made Hubble a cell phone camera. Just realize what you said.
It's a comparison.
That's just stating though how much advancement there has been. Right, when we can now compare Hubble with a cell phone camera versus a full, camera that you would use for like a wedding or something,
right.
Like that's crazy. That
I think
there's that much of a difference.
Is even bigger than that.
You think so?
Maybe cell phone cameras from 5 years ago.
Wow. Okay,
that's what I think.
Bold words.
Let's see. Let's go to the Southern Ring Nebula. There you go. Now this was my favorite one. This was the Farina Nebula. Right here. And the Farina Nebula is a star forming region. And Hubble's actually, it only does part of it, right?
Okay, because the camera size is different.
Right. Camera size is different, and I assume they mosaiced it together.
Sure, they did.
And I mean, even just with Hubble, that's gorgeous, right? That's
right.
A place where stars are being born. You can see the clouds of gas and dust.
You see those little eggs, those evaporating gaseous globules, which is the stellar nursery, the birthplace of stars, mm-hmm. Right? Yeah.
That sounds like a band name.
Eggs. Eggs is the acronym.
Okay.
Evaporating gaseous globules form stars. So eggs make stars.
Okay.
Isn't that weird?
That is weird.
Yes.
But then as you scroll over, you can see more and more detail. And my understanding is that you
go back there for a second. I'm seeing more structure at certain places in the Hubble image. Like, see those little, go back, keep going. Right there, right as you just passed it, that little like wispy thing that's coming out the top. That's disappearing from the image. And that's once again one of those things that it's not seeing it necessarily as a complete increase in resolution, but a different type of light. Mm-hmm. And that little wispy thing is obviously not hot enough to see it in the James Webb image.
Right.
Or vice versa.
It's
too
bright
hot
enough. It's in the light.
Right. It's a visible spectrum. Right. For
Hubble, but that reflected light is not in the infrared.
Exactly. Yeah. Other way around. You're right.
So we're seeing things differently. Like even look at this guy right down here. Right.
Yep.
We just move that over. Boom.
Yeah, you're just seeing much more detail in certain areas,
and you can see through that gas with the infrared.
So here I'm gonna put a pin in not just what is something that may look obvious, which is that there's a higher resolution here. There's actually not.
What do you mean by that?
If you read the media kit, it makes very clear that the resolution of James Webb is similar, almost identical to that of Hubble, but just in the infrared. What people are not taking into consideration, and these are NASA folks that are even saying this too, is that longer wavelength infrared waves, you need a bigger mirror to achieve the same resolution. So they designed James Webb Space Telescope to match the resolution of Hubble.
Really?
But in the infrared. So a lot of this structure and a lot of the messaging that they're doing here with this is actually kind of wrong.
It happens, yeah.
It's new information, but it's not necessarily higher resolution.
Okay.
Yeah,
It's looking at the same thing with a different lens.
correct. Different type of light.
Different type of light. Yeah.
Right.
Yeah. So this is a galaxy cluster with Hubble, right? Now this is not the ultra deep field, but it's kind of close, right? And you can see all kinds of little faint fuzzies, all different galaxies, and then we bring Webb into it. Boom.
Now, those little diffraction spikes, you'll notice that you see those spikes coming out of certain objects, but not others. Those that are showing us the diffraction spikes are stars.
Right.
Everything else is a galaxy.
Mm-hmm.
And now the reason there's a diffraction spike is because these are point sources of light where the actual structure of the James Webb Space Telescope is causing that to happen. You can see that there is a similar diffraction spike on that same star that Rob is moving it over right now from the Hubble, but there's less of them, and there's more with James Webb based on the construction of the actual telescope itself.
Yeah. I thought the coolest things that you can see in this one is look at all those gravitational lenses right there.
That's awesome.
Right. All those warped galaxies, right? And so anything in here that doesn't have those diffraction spikes is a galaxy.
That's awesome.
Right? I mean, that is just amazing, right? And I mean, this is a good picture. This is instructive. You get a lot from that, but you're going to get even more with that.
Cool. Let's move on.
And I think the last one.
Yes, Stephan's quintet.
Yeah. So this is Hubble. This is Webb. What do you think of that one?
Okay, so we've got a number of galaxies here that are actually not only in the same place in the sky, but they're also very close to each other in actual three-dimensional space. And you can see some of that tidal tail in the top galaxy there, Rob is highlighting right now, where there are a bunch of stars and gas and dust that have been kind of torn off of one galaxy as a result of the gravitational interaction, galactic cannibalism, as they call it, between these galaxies. So,
which you can kind of make out.
Make it out in the Hubble. And I'd say, look, once again, I'm going to kind of say what I was saying earlier about the different detail. It's not necessarily higher resolution, but just different details from one to the other. So Hubble is better in other ways.
Mm-hmm.
And I think that, once again, the messaging for that, of course, they want their new shiny thing to be the best,
mm-hmm.
but it's not really the purpose of it. It's not meant to be better than Hubble. It's different than Hubble.
Yeah. Yeah. They got to kind of work the difference there, right? Like, it is better in many different ways, but it's also different in many ways. So they got to,
right.
It's
a tool for every job.
Yeah.
Right. And this just happens to be the right tool for this particular set of science that we're trying to do.
Right.
Yeah.
So there are the pictures. I know my son and we watched the whole thing together, and it was cool. He was very excited.
So, okay. Question for you.
Mm-hmm.
If you had to choose an object that you would like to see with the James Webb Space Telescope, what would it be and why?
Orion Nebula.
Okay.
Right. We already talked about that. But yeah, because I want to see more, where are the stars in there? Right.
Okay.
Because you can see through the clouds, right? Probably also the Ring Nebula, right? Like, that's amateur astronomers get that, right? You can get pictures with your telescope with that. Hubble's taking pictures of it. What are we not seeing? What is in the infrared? What kind of extra clues do we have around that one?
So, you may not know this. Maybe you do. But you're going to get your chance to see that. You're going to get the chance to see the James Webb Space Telescope picture of the Orion Nebula.
Oh, I would hope so.
But here's why. In 1 year, James Webb Space Telescope will be doing an all-sky map.
Ooh.
That is the coolest thing I have learned, is that the James Webb Space Telescope is not just going to be looking at one little patch of sky like Hubble was. They designed it to have a very wide field of view, and over the course of about a year, it will be able to map the entire sky.
Nice.
Yeah.
Wow, that's going to be cool.
Right.
Put that on Facebook in a 360.
Right.
Right.
Or go to like, your VR space, your metaverse, right? You can check it out in the metaverse.
Oh, wow.
Yeah.
I wonder how deep that's going to go.
I don't know how much exposure time they're going to put on each of these images,
I don't think you can put a lot of exposure time.
Right. Without doing other science, you got, yeah. But that is one of those kind of like director of NASA type of decisions that's what they want to use it to do.
Well, I think that makes sense, because if you want to reach the public and you want to say, oh, here's this, here's that, I think it's amazing to just be like, here's one picture of the entire universe that you can look up, down, left, right, zoom in, zoom out, go at it.
Right. And we already have these all sky maps from other telescopes. It's not novel in that way. It's just that the resolution of that particular wavelength is going to be the highest ever we've ever gotten for this longer wave infrared.
Yeah.
Which is going to be good.
Yeah.
It's going to be very nice.
So then after that, it'll just take particular objects and do more.
Much more, right? More integration time, more time on target. And that's how you really gain much more information is sitting on a target for a long period of time, taking lots and lots of photos. And then just like in amateur astronomy, you stack them in post-processing and you get the best possible image out of it, which won't be possible for the full sky, of course. But you'll get these really good pictures still, nonetheless.
Yeah. Oh, that's cool.
Yeah.
That's awesome. I hope it turns out really, really well. Like, I hope it looks all well blended and, because you know how sometimes the pictures you can tell where the mosaics overlap or whatever.
Sure.
I would think they can do that pretty well.
Oh, they can do it very well, yes. So on my way out to the NSTA conference in Chicago, I had a chance to read through the basically the media kit for James Webb Space Telescope. So I thought I'd just share a few things about that. And the first thing I just want to kind of go over briefly is the science. So the James Webb Space Telescope science is categorized into a number of different categories. The first of these is the study of the early universe. And so for many people who saw the first images, we had that very first effectively Webb deep field image, and it was all the way back to the very beginnings of the universe. This time, just a few, 100 million years after the Big Bang, a place in the universe where we have never seen before because it was too far for Hubble and it was too recent for the cosmic microwave background radiation that radio telescopes are able to get us. And so it just was in this place where it was actually designed to meet that need, to fill in that missing gap in time. And so this is, for me, I think one of the more exciting things is that we are going to start to learn more about that era. And that era happens to be the time when we have to have galaxy formation, star formation for the first time.
Right.
So we know of a time we were able to observe times before galaxies and times once galaxies already existed, but we still don't have any way to know how galaxies form. And this is going to provide that knowledge all of a sudden. And so I'm excited to see what they come up with. So I went to the NSTA conference, and there I actually had the chance to hear from someone from Northrop Grumman who actually designed the James Webb Space Telescope and put things together for multiple countries, right, are involved. And they were talking about how some of the early pictures that we have now have a higher level of oxygen in the actual universe than we thought was going to be there. And I heard this and I thought to myself, well, how could that be the case, right? If that's in fact true.
Let me guess. I mean, high mass stars exploding?
Yeah, exactly what I said. So not just high mass stars, but stars, and this is my gut feeling, stars that are bigger than we've ever could have imagined. So big that they can explain supermassive black holes as well.
Oh.
That's my idea.
A single star creating a supermassive black hole.
Millions of solar mass star in the early universe, right? Because there's so much density in the early universe. It's so possible. The gas is so abundant, and
it would be short-lived because the bigger the star,
extremely short-lived, right? And so I just have this hunch that we're going to find out that there were early stars, supermassive black holes were formed from them, and that's why supermassive black holes exist everywhere pretty much. Is you had a number of these really massive stars, they blew up, and when they blew up, they created a supermassive black hole, and all the other dust and gas got swept up around them, the supernova guts effectively, and that's why we have more oxygen than we thought we should at that point, because it was created really quickly.
So what do you think then? Would that be... I would assume those supermassive black holes are still around.
Well, yeah, that's the same supermassive black holes that are in the middle of our galaxies.
So you're saying that the Cygnus X1, right? That's the supermassive one. Yeah. That one could have been made in like the first 300 million years of...
Right. And Sagittarius, our galaxy, Milky Way galaxy's black hole, Sagittarius A is also one of those. And pretty much every galaxy has a black hole in the center, we now know.
Right.
And so, I believe that we're going to find evidence, and this is completely just a hunch, that those early stars were that big. Or at least much, much larger, to the point where when they merged, that it was not many mergers were required, I guess, of black holes to form the supermassive one.
Wow.
That's
pretty cool.
That's my hunch. Okay,
cool.
And we'll see if it pans out. And I can't write scientific papers as a PhD because I'm not a PhD, but I can certainly put out a podcast that I can date.
Yep.
So as of this date, July 27th, 2022. That's my personal hunch. Okay. I won't call it a hypothesis, but that's my hunch.
It is. Is it a testable prediction?
I guess so.
I think it's.
I have somewhat of knowledge in this area.
Yeah.
Okay. I'll take it. Yeah. I'll take it. That's my hypothesis. I would call that a
hypothesis. Yeah, absolutely.
Okay. And then next up is galaxies over time. And so this kind of falls into that same boat, right? So galaxies are forming. We now know how galaxies are formed. And now we can watch how they evolve over time as they get closer to that era that Hubble has already informed us on. That's going to be the legacy of James Webb. We're going to get that data finally. We're going to know how galaxies evolve in a very similar way that we now already know stars evolve. Stars go through an entire life cycle. We don't know that information yet for galaxies. We should know after James Webb. Star life cycle. Once again, so stars early on in the universe, maybe they fall into this hypothesis that I have. Maybe they don't. Maybe I'm proving completely wrong. But nonetheless, we're going to start to have a better understanding of the life cycle of stars, especially stars that are those really tiny ones that we know last for the entirety of the universe, right? Those red dwarf stars. Yeah. So they would have been in their infancy in the early universe, and they're still around. So we can follow them along the way. So that's pretty cool. Other worlds. And please feel free to chime in on any of these, Rob.
Mm-hmm.
Other worlds, we're talking about stars that have planets that go around them. So these are extrasolar or exoplanets. And James Webb Space Telescope has a special coronagraph on it, which basically will be a shield of the ability to block out the light from a star so that you can see the planets going around it.
Mm-hmm.
And you'll be able to get some really good high resolution information from these. Now, it may not even be resolvable of the surface, but you will be able to see like the composition using spectroscopy of its atmosphere for planets that are going to transit in front of the star. And the amount of information that we're going to gather about these exoplanets that we've already discovered is going to be amazing. And from what I understand, it's James Webb is already looking into the TRAPPIST-1 system, which is one of our best Earth-like planet stellar systems
Mm-hmm.
that we know of. I believe it's 7 total planets, and 2 of which I believe it is that are just like our Earth, or very similar to our Earth.
Yeah, this was one of the things where the second picture that they showed in the grand unveiling, which of course my son and I watched as well. It was interesting because he was like, Dad, this is boring, but I can't stop looking.
I mean, the honesty of kids, right?
Yeah. I was like, yeah, they could do better. Sorry, NASA, but your production was a little disjointed there, but I get it. But anyway, he was watching, and the second picture was a graph. It was
Right.
a data graph, which to anyone who doesn't know much about space science and exoplanets, they would have looked at that and been like, meh, what does it mean?
Right.
Right. And I think they did a decent job of explaining that. And they said, we're finding planets and we're trying to see like, where is the oxygen? Where might we see liquid water, that sort of stuff. And I thought, man, that is really cool. But I didn't think the picture did it justice unless you had that base knowledge behind it.
I think that's where they could have done better, is they could have explained, well, what does this information help us understand, right? Yeah, it was.
I think they did a decent job, but I mean, they were looking at 5 amazing pictures, so
right.
They did what they could.
Right. Those are the main mission targets. I also did see that it can do things within our solar system as well.
That's what I was going to say too. Like, what are we going to find out? Because we've had telescopes on our planets for ever since Galileo pointed his telescope at the sky, right? Like, what else do you think we're actually going to find using the different wavelengths now? Like, what?
Right. And we're going to be into the mostly infrared with the James Webb Space Telescope, as opposed to Hubble, which was mostly the visible light spectrum and part of the near infrared.
Mm-hmm.
This is more into the like long wave infrared, which is a little bit different in just what type of things you can see exactly.
Yeah. I don't know. I was thinking, if we are looking, I was thinking maybe that would help us learn more about the inner layers of the planets. Because I know the question I always get is, what about Uranus or Neptune? Like, is it a solid core in the center? Is it molten? Is it, and I still feel like whenever I look it up, it's like, well, it could be this, it could be that, like maybe we can get better understanding of what the interior
I think you're
is.
still going to see just the atmosphere, unfortunately, because thermally the gas giants are pretty hot as you go down just a little bit into the atmosphere. It gets dense enough where they're heating up pretty good. And so I think you're still going to be limited to see, but you'll see different parts of the atmospheres, just deeper into the atmospheres for sure. But as far as it going down into the planets, it might be helpful in understanding like volcanism too.
Mm-hmm.
So if you have, for example, we are still unsure what's going on with Venus, right? Venus is potentially very volcanically active, and we have we don't really have a good way of finding that out right now. But the atmosphere there is like 800 degrees, so it might cause some issues as well.
Yeah.
Well, you never know, right? That's the whole question is, what are we going to learn that we didn't expect to learn?
Right.
I think one of the interesting things is going to be, how long does James Webb Space Telescope last?
Right.
What is the longevity here? And that's why I asked the question about Hubble, right? It launched in 1990. It is 32 years later, and it is still working. Granted, we had the ability to send people in space shuttles to fix it and adjust it. So that extended it. Webb, we don't have that.
Well,
It's up there.
That being said, the representative from Northrop Grumman, he was asked that direct question of, what about potential for repairing it? And he said, well, of course, that, as most of you probably already know, there is no plan to repair it. It's got about 10 or so years of the cryogenic material it needs to cool the camera sensors, because these are needing to be very cold, given that we're working with infrared or heat as our main target. One instrument requires it to be actively cooled, which means that we have that limited lifespan of about 10 years till we use up all that cryogenics. Or it could be somehow recharged, maybe. But that's the question. Are we going to be going out to do that? The other instrument, on the other hand, is passively cooled. And so at least one of the cameras actually will continue to function. And that is really a question mark. Everybody keeps giving the 10-year lifespan. As far as fuel goes, to be able to keep its spot in the orbit, the orbital insertion that NASA did was so good
Yes.
that they believe it's going to easily meet its 10-year. Like, it was supposed to be 5 years
Oh, really?
to 10 years. That was the goal. They think it's going to be well beyond 10 years now, and possibly even up to 20 years.
That's what I have written down here. I read that it was 10 years of science is planned,
Right.
20 years is expected, and then
Who knows?
right? I mean, we still get messages back from one of the Voyager probes,
Right.
you know, like a teeny tiny signal every now and then, but like we know where it is, and
Sure.
it showed us where the heliopause was, and that was launched in 1970, 1971, something like that.
Something like that. Yeah.
So like I want you to make a prediction now.
Okay.
Okay, let's do two. A, is it going to be serviced in the future?
Yes.
Okay.
They're not going to waste all this money.
Need to get there though. So
Hold your horses. Here's what the Northrop Grumman guy said.
okay.
He said they've got some amazing robotic systems that are going to be. They've been challenged in ways that are similar before, and he said, "I don't see why a robot couldn't refuel or repair James Webb.
Okay.
They know everything about it. They just need to be able to get a robot out there, and that's just another rocket launch."
How about this? I'll say not until the 2030s.
Oh, I don't think they're going to need, hopefully,
Well,
to
they
do
won't
that.
need to, but yeah, I don't.
Right.
Yeah. Interesting.
And you'll have
Okay.
some of these very large rockets that, the likes of SpaceX and Blue Origin at this point
Yeah.
have in development. And we've got SLS with the Artemis, like our last podcast, we talked about Artemis. Those are going to be actively online systems. I don't see why we wouldn't. I think that it would be a waste for them to just let it
True.
sit.
Yeah, I wouldn't see it happening for the next 10 or 15 years. Though.
Right. And
Plus,
like I said,
also, you
hopefully they
gotta-
won't need to.
Yeah. And also, you got to think about how long it took Webb to actually be planned, built,
About
constructed.
30 years.
Yeah.
Yeah.
And so
Right as soon
even
as they
if-
got Hubble up,
Yeah.
they had already had this one on the drawing boards.
And so even if you give 10 years till they want to do it, it might be 20 before they actually get to launch something and get it up there. Now, it's not as make or break as actually putting up the Webb telescope, but still, I don't know. I feel like there's going to be more mountains in there than what we think right now. But
Right.
I think it'll be good. And the question is, how long until it goes completely?
Yeah.
I don't know. I would think 30 years.
Right. I think it's probably until they just make something that's that much better too.
But then I looked up Spirit and Opportunity, our twin rovers on Mars, right? Do you remember how many days were planned?
No idea.
90.
Ah,
90 days. 3 months were planned for that thing. And I have that Spirit lasted thousands of extra days. And Opportunity, who just passed on June 2018, that was 5,000 plus days.
wow.
So you're talking that it lasted what, 50 times longer than expected?
And those ran off of solar power.
Yes.
Guess what? So does James Webb Space Telescope.
Yeah.
That is a big deal. So when something's running off of solar power, it is really, the limitation of the hardware, not a fuel source for those things.
Mm-hmm.
The fuel source, of course, of keeping it in orbit, it's a different story. But,
Mm-hmm.
if you have like a plutonium source, like the newer rovers do, then you do have a limited power source that will eventually run out, period.
Didn't Voyager work
Yes.
on Pluto? And
It's
that's
still running.
And,
Well, it's
and we engineer it so that it doesn't need as much to run because of,
right. I mean, you always want to do that.
Mhm.
Yeah, for sure.
So, I mean, I'm just super excited about this because of the stuff that we don't even know that we're going to find out. I'm excited to see what what we're doing with the age of the universe, and the fact that Webb will be able to see back to about 100 million to 250 million years after the Big
Bang, yeah.
Right. And that's because it's doing the infrared stuff.
Right.
And I think there's other things out there. Like, we're not going to be able with Webb to see the very beginning. Right?
No, it's not designed to do that.
It's not designed for that. And that's something when I was looking up, I was like, man, we're going to get this refined. It's like,
but we already do have that with the cosmic microwave background radiation and radio waves. We don't need it. We already knew that stuff. It's this weird, like, missing link. It's the Bigfoot of the universe, right? We're trying to figure out what happened in that gap, right? So I really do think that we've got a really great future for James Webb. I will say, I did ask also the Northrop Grumman guy. I said, what about potentially just reusing this design? How hard would it be to just make another James Webb now that we've made one? And to follow that up, I said, with the larger rockets that we are currently in the process of developing, launching soon, what about scaling it up, making an even bigger James Webb type space telescope? And he said, the real thing is the design is now done. As you said, it's dollars, it's financing it. He says that's the biggest challenge. It's not an engineering design challenge anymore. That we've already determined and figured out. And as far as scaling it up, he said this is only about 80%. I think he said about 80% the size of it could have been within that launch vehicle.
Oh, really?
They could have actually gone a little bit bigger, but it was budget that they caused it to slim it down. And so they could have already gone bigger. And then we're going to have these massive, rockets that are going to be able to support, I think it's like 9 meters across, whereas the current fairings on rockets that, like this one, the Ariane rockets that this was launched on, are about 5 meters. So we're talking almost double the diameter. You could put a massive telescope that folds up just like this inside. So I think that is what's going to kill off James Webb. I think you're going to see the development of a space telescope that makes James Webb look tiny.
Well, okay.
Just like James Webb makes the Hubble look tiny.
Yeah. I wouldn't see putting up another one. I don't think that would make much sense.
I don't know of a reason why, if this does its mission properly, because this is going to have
almost exactly the same as James Webb. Maybe in like 10 or 20 years, as this one starts limping along, launching another one. Maybe, but we didn't do that for Hubble.
We did do it with the Curiosity rover and now the Mars 2020 rover, though. Yeah, it's almost an identical chassis. The instrumentation on board is different.
Okay.
So if there's a development of new instruments, different types of instruments that they could put onto it and do a different job.
That's true. Yeah, make it different enough.
Right, that it does different mission.
Can you have two at the Lagrange point?
Yeah, there's tons of spacecraft at the L2. Yeah.
Oh, really?
Oh, yeah.
Oh.
Yeah, this is not a single... Space is pretty big.
Well, that's true.
They just put it in orbit,
that's right. It's in orbit around that.
Orbit around L2, yeah.
So then you can have multiple...
You can have a bunch.
Really?
Not unlimited, of course, but you can have a bunch.
Huh.
Yep.
Didn't think of that. Nice.
So, I think that's what's going to take... eventually take James Webb out of commission is aging / new developments that are going to just make it look tiny.
But we're not there yet.
We're not there yet.
So Webb's amazing, right? It's going to be looking at the sky with different eyes, right? I'm excited to see, first off, things in that different light, but I'm also excited to see what are we going to learn that we didn't expect to learn.
Let's do a follow-up to this, maybe a year out from now, and just kind of see, looking back, at what our hopes and dreams were for James Webb, in the meantime, what has happened. So, let's look at next summer, next July or something. We'll try to get together again for another podcast, and we'll talk about 1 year with James Webb.
Yeah.
Okay. And I think by then you'll start to see some of the other science coming out as well, and we'll be able to dig in a little bit deeper with that. So once again, this is our Cosmos Safari podcast. I'm Dave Farina. This is Rob Webb. And we're going to bring the universe closer than you think. Thanks for listening, everybody.
All right.
Take care.
Sounds good.
Keep looking up.